Today we talk about zkSQL, verifiable and efficient query evaluation with zero-knowledge proofs. This is Xiding Li from Northwestern University. Here is our agenda. As we know, relational DBMS are ubiquitous. The goal of this work is to construct authenticated query answer without divulging private input data. We use college rankings data as a motivating example. From these two recent news, we know forged data lead to inaccurate rankings. We want to provide a strong assurance that the statistics from each school are accurate and complete. From another side, we know data breaches are also terrible. Data owners don't want to review private information. Also, regulations on data privacy expose data owners to further liability when they answer queries. Now it leads to a dilemma. How can users obtain trustworthy statistics without data providers sharing their private records? The users are not just the DOE or US News. In the medical case, users could be hospital or patients. In this work, we use zero-knowledge proofs to break the stalemate. Our contribution is zkSQL is the first work for ad hoc SQL queries with ZKP. We have operator-at-a-time proofs for a given query plan. We have set-based protocols for proving properties about the intermediate result of an authenticated query. Finally, we have experimental results on TPSH benchmark demonstrate improvement up to 2 orders of magnitude over the pure circuit baseline. Then what is a zero-knowledge proof? In a ZKP, the prover convinces the verifier that a statement is true without revealing any additional information. In motivating example, a university is the prover, and the DOE or US News is the verifier. There are 2 common cases in ZKP. The first one is prover proves to verifier that a statement C is true over a witness W for a computationally hard problem. The other one is ZK protocols can prove multiple interrelated facts over W. zkSQL builds on top the commit and prove paradigm. For the paradigm, we have ideal functionality FZK. For commit stage, we convert private inputs or constant into commitments. For proof stage, compute queries queue for authenticated results, and verify confirms the integrity of the circuit. It returns false when cheating detected. Now we talk about ZKP in query evaluation. In this problem, prover has a private database D. Prover and verifier wish to evaluate query Q to prove authenticated query answer A. zkSQL guarantees correctness, soundness, and zero-knowledge properties. zkSQL uses state-of-the-art vector-oblivious linear evaluation ZK protocols, but it generalizes to any interactive protocols. It is scalable to large inputs and composable for complex query logic, so well-based protocols instantiate FZK. Our first step is zkSQL translates Q into circuits one operator at a time. It takes 5 to 6 orders of magnitude longer than plaintext query evaluation, which is high overhead. We improve performance up to 2 orders of magnitude with set-based proofs over intermediate query results. Then we talk about the security model. We use universal composability. UC is a general framework for proof security of cryptography protocols. It proves strong guarantees and allows protocols to be composed arbitrarily. zkSQL constructs proofs for ad hoc queries using UC-realized protocols. A malicious prover cannot sabotage integrity of query evaluation. A malicious verifier cannot obtain any unauthorized information about D. New operator-level protocols designed in the future with UC-realized proofs can be added to zkSQL without altering security guarantees. In order to remain zero-knowledge property, proof evaluation is oblivious with respect to operator control flow. In this work, each tuple in D bracket has a dummy tag. Dummy tuples do not contribute to query answer. It prevents data access pattern leakage. From this end, verifier knows schema of relations, cardinalities of intermediate results, operator execution order, and the query answer. Now we talk about architecture and workflow of zkSQL. First, the prover commits private database D. Each party I holds their partition. Verifier alone additionally holds an authentication key. No one can deduce commitment of the other party. Prover only commits D once for all zkSQL queries. Then is authenticated query evaluation. First, the verifier sends query queue to prover. Prover and the verifier interactively evaluate the query in zk-SQL. During interactive proofs, prover has dual representation, plaintext and commitments of the query data, including interactive results. Verifier works only on its commitments. Finally, prover sends authenticated answer A and proof to V. Verifier can verify the answer with the proof. Here is the workflow of zk-SQL, and I will introduce it in the following slides. First, zk-SQL parts query queue into a directly acyclic graph of operators. We use Apache CalSet. We support filter, project, join, aggregate, and sort. zk-SQL has a protocol template for one or more algorithms for each of these operators. Then zk-SQL uses Volcano-style transformations to convert the DAG into a zk-friendly execution plan. There are rules including projection pushdown, filter merge, and a sort for group by aggregate. For verifiable plan, zk-SQL maps each DAG nodes to an operator template. It maps the operator with its parameters into operator instance. It compiles this to form a sequential verifiable plan. For leaf operator scanning table T, we instantiate this as a scan over the commitments T bracket. Prover and the verifier interactively execute the verifiable plan one operator at a time in the backend. Before moving to zk-SQL protocols, we show baseline results. Protocol of each operator directly translate to corresponding circuits using standard DBMS logic. It shows 5 to 6 orders of magnitude slowdown over unauthenticated query evaluation on TPCH benchmark. Instead, zk-SQL delegates some steps to prover. Prover and verifier interactively verify intermediate results from local computation using set operations. It is up to 2 orders of magnitude improvement. We know baseline approach is not sufficient to be practical. In zk-SQL, we introduce set operations to verify intermediate results locally computed by prover. We support 4 set operations: equality, disjoint, intersection, and union. Simulation-based proof guarantees zero-knowledge property. Then we discuss protocols of set operations. The protocols zkSet securely realize the functionality fzkSet in the fzk-fzkSet hybrid model. zkSet represents each tuple as a bit string of m bits. For tuples with m larger than 128 bits, zkSet protocol packs them into 128 bits. zkSet protocol represents the proof in polynomials. Each set operation has complexity O of m. Now we introduce protocol for each operator in zk-SQL. We realize fzk-SQL in the fzk-SQL hybrid model with the protocols circuit and setup. Circuit protocol evaluates operators in pure circuits over commitments, like the baseline approach. Setup protocol is a mix of circuits and set operations. T outputs from each operator either an intermediate result or the authenticated answer A. Circuit protocol contains project, filter, and aggregate operations run in zk circuits. It directly translates from its standard DBMS logic. A prover and a verifier interactively prove a tuple at a time from input R. The protocol does not benefit from set operations. Setup protocol is to improve pure circuits approach. In baseline with n input tuples, oblivious Platonic sort takes O n log square n. Oblivious nested loop join takes O n square. We optimize protocols up to O of n with zkSet protocol. It implements equal join and sort. Protocols consist of both circuits and set operations. Verification of prover's result. It verifies set relationships of input-output tables and proof properties of tables. For sort operator, first the prover locally sorts R to T with respect to sort definition and commits T into T bracket. Sort definition is a set of sorting order for some attributes of R. We have 2 verification. First order verification checks each adjacent tuples in T are monotonically ordered with respect to sort definition. Then set equality verification check if R and T have exactly the same tuples. For equal join operator, first the prover locally joins R and S with respect to join predicates P and commits T into T bracket. We have three verifications. First, predicate verification, verify all output rows satisfied predicate P. The second, set difference verification, check no spurious tuples added by prover. Finally, we have disjoint verification. We know T has all output rows. Now we discuss experiments. We implement zkSQL on top of EMP Toolkit. We evaluate zkSQL over TPCH benchmark. We choose queries varying degrees of complexity. We scale TPCH database into 3 sizes. We set up 2 AWS instances, one for each party. We use runtime, memory usage, and communication costs between parties as metrics. First, we measure commitment cost based on 60K rows. The commitment for each table is a one-time setup for all queries. Compared to cost of experiments, the cost of commitment is minor part of our overall cost. We then test oblivious querying overhead. We remove padding dummy tags, which leaks intermediate cardinalities, performance proportional to true intermediate result sizes. We know dummy rows are necessary to keep obliviousness. We then investigate zk set performance and pure circuit baseline. From the table, we know proving set relationships about the result is more efficient than tracing the evaluation in circuits. Queries with more source and joins benefit more from the improvement. TPCH queries gain approximately average 2 orders of magnitude improvement. Now we go deeper into operator level. We use Q3 as an example. Project with column reordering and filter takes minor cost. Math expressions are expensive in circuits, such as project revenue and aggregate. Sort is expensive because of oblivious compare swap. Joins dominate runtime, about 57% of Q3 runtime. We then test the performance with varying network bandwidths. We conclude zkSQL is insensitive to network conditions. Then discuss scalability. Except Q9, all other queries doubles their runtime as input sizes approximately double. CPU time is proportional to runtime as input sizes increase. Q9 occupies most memory among all queries. Communication costs scale linearly with change of input size. Finally, we analyze financial cost. In zkSQL, cost of proving queries grow linearly as input size increases, except for Q9. Here are some related works. CrackDB and VariDB rely more on trusted hardware, where leak some information on program traces. IntegrateDB and VSQL use cryptography verifiable computation in outsourcing setting. They guarantee integrity, but not privacy and zero-knowledge property. So ZK extension of VSQL provides ZK proofs, but it does not support ad hoc queries. In conclusion, zkSQL is the first work on verifiable and efficient query evaluation with zero-knowledge proofs for ad hoc queries. zkSQL authenticates its query evaluation one operator at a time. Our set-based protocols improves the pure circuits counterparts, up to 2 orders of magnitude speed up on TPCH benchmark. Owing to universal composability, zkSQL is extensible to new operator protocols. Thanks to listening my talk. For more information, please read our paper, and any question, please send to my email. Thanks.